Welcome to the video of Hardware Interrupts of 8051, Assembly Language Programming and Simulation of this program using Kill software. So as you know, there are 6 interrupts in 8051. So first interrupt is reset, then timer 0, then timer 1 interrupt, and now here we are going to discuss about external hardware interrupt, that is INT0 for pin 12, that is P3.2 pin of 8051. And the address, interrupt service routine address for INT0, that is external hardware interrupt 0, is 0003H. And second external hardware interrupt is INT1 pin 13, that is P3.3, and whose interrupt service routine address is 0013H. The last interrupt is serial communication. So here we are going to discuss about this external hardware interrupt INT0 and external hardware interrupt INT1. So 8051 has two external hardware interrupts, that is INT0 pin number 12 P3.2. Here to cause the interrupt, user has to connect external signal to this particular pin, that is P12. And the second is pin 13, that is P3.3, which is called as a INT1 interrupt. So both are active low interrupt, and there are two types of activations for this external hardware interrupt. So to activate interrupt, we can either use level triggered interrupt or edge trigger interrupt. So we'll discuss both of this one by one. This is a conceptual diagram to understand the working of external hardware interrupt. This diagram is for INT0 interrupt, which is at pin 3.2. So we can use level trigger interrupt or edge trigger interrupt. Level trigger interrupt means we have to give a logic 0 at pin. So internally there is an inverter. Signal will be given to microcontroller, which will cause the interrupt, and microcontroller will execute interrupt service routine written at fixed address 0003H. So this is the level trigger interrupt. First we'll discuss about level trigger interrupt, and then we'll go for edge trigger interrupt. So we have to maintain a logic 0 for some particular time period to use a level trigger interrupt concept. So this logic 0 should be given to INT0 or INT1, same for INT1 pin. It should be connected to this external hardware pin for at least 4 machine cycles. So minimum duration is 4 machine cycles. For 4 machine cycles, user should connect the logic 0 to this particular pin to occur this interrupt. So if the microcontroller frequency crystal we are using of 11.0592 megahertz, then the clock for one cycle is 1.085 microsecond. So for 4 into 1.085 microsecond, the signal should be low at this particular pin. And after that, the user should give this logic 1 signal to this pin. But user, this is the minimum duration which is required to cause the interrupt. You can apply 0 for longer time period also, but this pin should be pulled to high before the last instruction of interrupt service routine. Otherwise, microcontroller will think that second interrupt has occurred, and it will again go for interrupt service routine. So before last instruction, that is return from interrupt, RETI instruction, this particular interrupt signal should be pulled to logic 1. Otherwise, the same interrupt will cause again. So this is for level trigger interrupt. We have to pull this pin, INT0 and INT1 pin to logic 0 for at least 4 machine cycles. Same for INT1, that is at pin P3.3, then level trigger interrupt. Here ISR routine is I0013H. Now this is the register we are going to use, that is interrupt enable register. Bit 1 is used for INT1 and TCON.3 bit also we are using here to select whether edge trigger or level trigger, so that we will discuss. So again for this interrupt one, this terminal should be kept at logic 0 at least for 4 machine cycle, and before execution of last instruction of interrupt service routine, this signal should be pulled to logic 1. For each trigger interrupt, the interrupt will cause while there is a transition from high to low. So when we apply high to low pulse to this terminal, the interrupt will occur. So you can say that at falling edge of the signal, the interrupt will occur. So initially the all port pins, this is pin 3.2 suppose. So initially all these port pins of 8051 are at logic 1 level. So when you pull it at logic 0, the interrupt will occur and microcontroller will execute interrupt service routine written at this particular address. So for each trigger, interrupt will occur when there is a transition from logic 1 to logic 0 level. For level trigger interrupt, we have to give a logic 0 signal for at least 4 machine cycle period. So when high to low signal is applied to pin, controller will be interrupted and forced to jump to location to the vector table to ISR, that is fixed ISR routine. So this is the concept of level trigger and edge trigger. You can use any of this type. Then the registers associated with this interrupt. So first is TCON register. So lower 4 bits of TCON registers are used for interrupt. So bit IE0, this bit, and IE1 bit. So IE0 bit is for external hardware interrupt 0 and IE1 bit is for external hardware interrupt 1. So when there is a high to low transition, that means when the edge of the signal is detected, that is high to low transition is detected, then this bit is set to 1. And when interrupt is processed, that means interrupt service routine is executed completely, this bit will be automatically set to 0. So this I0 and I1 are set and reset by microcontroller. When there is a detection of edge trigger interrupt, these bits are set to 1, and after providing service to that particular interrupt, these bits are reset to 0 by microcontroller. So these bits are used by microcontroller, set or reset by microcontroller. This IT0 bit is again used for external hardware interrupt 0 and IT1 is for interrupt 1. So using this bit, we can set whether we want a level trigger interrupt or edge trigger interrupt. When this bit is 0, you can use level trigger interrupt. When 1, you are using edge trigger interrupt. By default, this bit is 0. That means by default, the level trigger interrupts we have to use. And when you, if you want to use edge trigger interrupt, you can set this bit to 1. So this is for both the interrupts, hardware interrupt 1 and hardware interrupt 2, or 0 and 1. The next important register is interrupt enable register. So this bit is important, EA. It is used to enable the interrupt. So any interrupt when you are using, this bit should be set to. So any interrupt when you are using in your program, this bit should be set to 1. So IE.7, this is the D7 bit of interrupt enable register. So IE.7 register bit, IE.7 bit should be set to 1 whenever you want to use any interrupt. Here we are discussing about external interrupt 0 and external interrupt 1. So EX0 is the bit to enable external interrupt 0 and EX1 is the bit to enable external interrupt 1. So you can enable this bit to 1 and if you are using external interrupt 0, set this bit to 1, and when you are using external interrupt 1, set this bit to 1. This register is bit addressable register, so you can set individual bits separately, or you can initialize this 8-bit register. So now I'll explain the program for this program statement. Here program statement is read data from port 1 and send it to port 2 continuously. So we have to write a program so that microcontroller should read a data from port 1 and send it to port 2 continuously. While doing this, if external hardware interrupt 0 occurs, then complement the data of port pin P0.0. So whenever hardware interrupt occurs, then the data at port P0.0 we have to complement. So if it is 0, it becomes 1. If it is 1, 0. So starting address of program is 000H, that is the reset address. So here we'll write instruction ljump main. So directly we will not write a main program at this address because there may be the overlapping of main program and ISR routine program. So always whenever you are using interrupt, always write this ljump main instruction. Main is the label of this sub program, the main program. So at this address ljump main, so it will jump to main label, and at address 0003H, which is the address of ISR routine of INT0 interrupt. So here also we'll write instruction ljump to ext0. ext0 is the label given to ISR routine. So whenever you will turn on the microcontroller or reset a microcontroller, it will come to this address and it will execute this instruction and it will go to main label. It will execute a main program, and whenever external interrupt occurs, it will come to ISR routine. So it will come to this address and then it will execute instruction ljump ext0 and it will jump to ext0 label and it will execute ISR routine. So at address 0030H, so this address is considered here because this comes after end of all interrupt service routine addresses. You can use any address 0100H. Here we'll write a main label. So main program will write here. The P1 port we are using as an input port. We want to read a data from P1 port and send it to P2 port. So P1 port we are using as an input port and P2 port we are using as an output port. So whenever we are using port as an input port, first we have to write FFH on this port. So all port pins must be at logic 1. Here I have used this instruction clear TCON.0. It is to select a level trigger interrupt. If you want to use age trigger interrupt, here we have to use instruction set bit TCON.0. So TCON.0 bit we are now resetting to 0 to select level trigger interrupt. There is no need to write this instruction because by default a level trigger interrupt is selected. But to clear that particular bit, you can add this instruction. Then we want to use external interrupt, so we have to enable the bit for external interrupt 0, which is in I register, that is I.0. So for enabling this interrupt, external interrupt 0, set bit I.0 instruction is used here. Then set bit I.7 it is to enable all interrupt, global interrupt enable. So that is this. So this is the 8-bit of interrupt enable register. So that also we are set to 1. Then after that, we are reading the data from port P1 and storing it in accumulator. An accumulator data we are sending to port P2, and here it is written as jump here. Here label is given to this instruction. So microcontroller will continuously execute this loop. It will read a data from port P1, store that data in accumulator. Accumulator contents are given on port P2. So continuously it will execute this instruction. But since we have enabled this external hardware interrupt 0, it will check the interrupt signal available at this pin. And whenever interrupt occurs, it will go to interrupt service routine address 0003H. At 003H, we have written instruction ljump to ext0. So it will come to this ext0. We'll write this ext0 label or this program after the completion of this main program. Or you can write at particular address, you can give here org and address, but better to write this instruction after the main program. So this ext0 is the label given for the program of interrupt service routine. Here we want to just complement the data of port P0.0. So here instruction is written CPL P0.0 and the instruction is RETI back to return back from interrupt service routine. So it will come to this loop because it is continuously executing this instruction. Whenever interrupt occur, it will go to ISR, and after this return instruction, it will come back to this loop, and this is the end. Now we'll see how to simulate this program using Killsoft. So already I have copied this program and stored here. The same program is written here. So I'll save it again. We'll build the program. You can watch software introduction video to know how to write and execute this program, build, debug this program using Kill software. So no error is there. So click on debug and we'll start a debug session. Now click on peripheral and we'll check the IO ports. So this is port 0, port 1 also we want to track, port 2, here interrupt, this P3.2 interrupt we are using INT0 interrupt. Here vector address is also given. So this we are using. We can observe here while executing this. So I'll execute this program step by step. So debug step, that is FL11. So here P1 port is at FF1. IE bit is set, IE.0 is set to 0. Then it will read a data from port P1. It will be stored in accumulator. We can change the data of port P1 and we can observe where the data will be given to port 2 or not. So here we can observe. So I am pressing F11 for step-by-step execution. So here the data should be available at port P2. So same data, it is reading data from port P1, same data you will observe on port P2. And it will continuously execute this loop. F11 I am pressing and the loop is executed continuously. Now when interrupt occurs, so interrupt is level trigger interrupt and it should occur at port P3.2, port pin P3.2. So I'll insert this port 3 also, and this pin is port 3.2. I will give a logic 0 at this pin. That means now interrupt occurs and we'll observe whether port 0.0 bit is complementing or not. So I'm executing again program step by step. So it has jumped to this ISR routine at address 003 and then it will go to this label. So the label, the instruction is complement P0.0. So P0.0 should be 0. So we'll check that. So it is 0. P0.0 is 0. So it has executed. Now we should pull this pin P3.2 to logic 1 before execution of RETI instruction. Otherwise, it will think that again interrupt has occurred and it will go to interrupt service routine. So I will pull it to high. I will apply logic 1 manually and will execute this step by step. So it has returned back to main program and it is executing main program loop. Again, if you give this interrupt signal, it will go to interrupt service routine. You can check it. It will go to interrupt service routine. Again, it has come. Now, since I have not pulled this P3.2 to logic 1, it will think that there is an interrupt and it will go to interrupt service routine continuously. See, it is going to interrupt service routine because P3.2 is at logic 0. So this is how you can simulate this program and you can check this external interrupt. So thank you for watching this video.